So next up is actually myself. I'm Rachel Abel and I'm with the Department of Agriculture and Fisheries. And I'm actually here today and I'm going to be talking to you about bioreactors. Particularly bioreactor, I'll just start my timer, denitrification bioreactor walls, which remove nitrogen from shallow groundwater. Now, as Rainier pointed out earlier, nitrous oxides can exceed the water quality guidelines, and they do. And with targeting the groundwater, we're going to reduce that base level of NOx and we're not necessarily targeting the peaks. Now, importantly, in the Pumicestone Passage and the catchments that come into it, the soil type there is an old soil, it is a high sand, and it is a low organic matter soil. And essentially what that means is even very conservative programs of nitrogen are going to have likely to have nitrogen leach out the bottom at some point in time into the groundwater. So this here, we have an image of how a bioreactor wall may sit in the landscape. Now we have the crop up here, and when there's a rainfall event, what we'll find is the water will leach down through the profile because the infiltration rates are huge. They carry with it some nitrogen, which moves in the groundwater. In our soils, we have quite often an impermeable clay layer at the base at some point in the profile, and the water will then move laterally. And we can then intercept this water with a perpendicular wall of a high carbon-rich substrate. And in that wall, in an anaerobic environment, when it's full of water, it creates a really exceptional space for denitrification, so converting nitrous oxides into the harmless nitrogen gas. And the water then can come out of the bioreactor and continue to move on in the landscape. I now have a video for you, which is of the bioreactors which we constructed in June 2017, and they are the two longest operating, continually monitored bioreactors in Australia, and they're in our very own Glasshouse Mountains. The site was selected at the base of a gentle 9% slope under a pineapple crop before the water enters a tributary into Coochin Creek. Now, as I said, the soil type is essential for the success of wall bioreactors. Texture contrast soils are ideal as they have sand into that impermeable clay layer which forces the water in a lateral flow. At this site, the clay is 1.2 metres below the surface, and that governs the depth of the bioreactor. In deeper soils, we might need to be looking at other engineering options to make sure the walls don't collapse prior to the addition of wood chip into the reactor. The size of the bioreactors that we put in were approximately 20 metres long by 1.4 metre wide by 1 metre deep. The width of the bioreactor matched up to the width of the excavator bucket, and that was just for ease of digging. One of them was filled with a hardwood, eucalyptus species, while the other one was filled with a pine softwood. Both substrates are excellent at denitrification. However, the softwood is the preferred material primarily because it had a lower flush of dissolved oxygen during startup or after installation, and it had a null impact on the greenhouse gases. It is essential to ensure that bioreactors can intercept the groundwater flow. Ideally, the wall should be placed perpendicular to the groundwater flow, and so you do need an understanding of what's happening under the surface prior to installation. Wood chip is an excellent substrate in these systems because it also has a higher hydraulic conductivity than the surrounding soils. So this means that water will preferentially flow into the bioreactor rather than bypassing the system and not going through the opportunity to be denitrified. Alternative carbon sources can be used, although the hydraulic conductivity must be considered to ensure there's no bypass flow. You can see the geofabric being laid here on the surface. That was to ensure that the soil didn't contaminate the wood chips, and the plastic over the top was to protect the rainfall from coming in or any surface flows. In an unmonitored situation, those products aren't required. You can also see the PVC pipes there. They were piezometers, so water can flow in at the bottom at depth, and we can sample, we can test for groundwater height, and we tested in the upslope, which is the incoming water, so we can understand what's coming in. We tested in the middle of the bioreactor so that we can understand what's happening right in the centre, and we also tested the effluent, so we know what's happening once the water leaves the bioreactor. Bioreactors, they begin to function immediately, basically, as soon as the wood chip becomes saturated. After extended dry periods, the bioreactors return to function quickly, though a lag is noticed. And it's not known whether it is a depletion of the microbial community during the aerobic period, or a shorter hydraulic residence time during the early stages of saturation. There is research being conducted into the seeding of bioreactors to improve efficiency. Now, the results I'm about to present, they're from this paper by Dr. Fabio Manca. This is the published work from the first 2 years of results from the two bioreactors. So if you've any further interest, this is definitely a place to go. So we had removal rates which ranged from 0 to 5 grams and 0 to 5.7 grams in the hardwood, and that's grams of nitrogen removed per cubic metre per day. On average, over the time, while the bioreactor was functioning, it was 2 grams for the softwood and 1.6 grams of nitrogen per cubic metre per day for the hardwood wall. Sorry. Now, the other thing that I'd like to point out is around greenhouse gases. Both walls emitted lower CO2 equivalents than the natural environments, and the softwood wall was producing null emissions while the hardwood wall was 65% higher than the softwood, but still lower than the natural environment. And just to give some context around those removal rates, in the published data, they've had from 0 to 12.7 grams per nitrogen per metre per day. The highest value was a sawdust wall receiving over 60 parts per million. And in some of the cooler climates around the world, they are very happy getting 2 grams of nitrogen removed per cubic metre per day. And that's as their top rate. This is an image of the bioreactor in January this year. The buckets are there to protect the piezo's from UV and being mown over for the maintenance. The things that influence the removal rate of denitrification, or the removal rate and denitrification, include the hydraulic residence time. You actually need the water to sit in the bioreactor for somewhere between 6 and 24 hours for sufficient microbial denitrification. It does depend on the incoming water. And so the concentration and also the temperature. Higher temperature, increased microbial activity, increased rate. Increased nitrogen in the water, increased rate. Now the wall bioreactors are advantageous against other treatment systems where land availability is limited. Is an excellent edge of field treatment because ultimately in an unmonitored situation you could drive over the top of that if required. Around the state, bed bioreactors have also been investigated for surface flows, and we've also looked at attaching bioreactors to point sources. Now, point sources in agriculture might look like tile drainage under the ground, attaching to the end of that, or if there's an intensive farming system in covered cropping where there's an outlet, you could plumb one up to the outlet quite easily. Outside of agriculture, any point source of N has the potential to be helped by bioreactor technology. What does it cost? This is the only paper on economics. It's a US paper by Laura Christensen. What this shows is looking at the on-farm nitrogen practices can actually save you money. Now, that's what I spend the vast majority of my time looking at when it's not bioreactor, and also later when we have the panel, Tim Wallens is going to be talking, and that's what he spends a lot of time doing, research on farm to work with the practices of the grower, identifying what can be improved. Is there something we can improve, and how can we improve it? Cover cropping and crop rotation, they are quite expensive to use. But from a catchment management perspective, for all the catchment managers out there, we have controlled drainage, wetlands, and the bioreactor that they've said have all come in quite evenly at a cost of $3 per kilo of nitrogen removed. Now, we had a nitrate limited bioreactor. Our estimate is the bioreactor that we installed is costing around $10 per kilo of nitrogen removed over time. If we had more nitrogen coming into it, it would have increased, that number would have decreased. I would like to, this is the end for me, I'd like to acknowledge Adam and Gary Pike of Pikes Pines. They supplied the land and they supplied the excavation material, and without them it would have been not possible. I'd like to also thank the Queensland Department of Environment and Science for funding the investing in our Environment for the Future program, which all of this work was funded out of. I'd like to thank QUT, who supported Fabio in his PhD in and around this bioreactor, and of course I'd like to thank DAF, who has been managing the program. If you want to find anything else out more about bioreactors, and those two papers mentioned haven't sorted that for you, the wetland further resources there, that is a fantastic place to go.